Hello everyone. In the previous lecture, you guys learned about the basic bridge inverter, and today we'll be walking through a real-world example. So many of you may be too young to know what this is, but a long time ago, your cars would offer a 12-volt DC power outlet. And this is known colloquially as a cigarette lighter. Now you could use it for that application, but today we'll be showing a different one, namely an inverter. So you plug this in, and this would convert that 12-volt DC input to 120 volt RMS AC output voltage, and this is meant to emulate sort of a fake grid. So you could plug your devices like laptop chargers or phone chargers into these outlets, the output of the inverter, and use it like you were plugged into the wall, only when you're in your car. So this is what our inverter looks like when you open up the packaging. And here we have a simplified schematic. Now this should look fairly familiar. So we have our DC input, and then we have a flyback converter, which provides isolation and steps up that voltage to a high voltage DC. And then we have a full bridge unfolder to provide AC to the output. Now if we look at some of the major components, in the middle here, this large component is the transformer, and we can see the windings, and it's wrapped in a yellow insulation material so that there's no arcing or short circuits because it is operating at high voltage. And then here we have the 4 unfolder switches, and in the follow-on to this course, so 213B, you guys will get the opportunity to build your own power converters and design your own circuit boards, and you'll gain some experience and learn how to select components such as these. Now today, we're going to walk through some waveforms of this converter on the oscilloscope. So we have the input voltage in green, the switch node voltage in pink, and the output voltage in yellow. So we can pull up the oscilloscope waveforms, and we can power on inverter. Volts. And here we are. So you can stop the waveforms and look at our measurements. All right, so I mentioned the input voltage is in green. You can see that here. That's a steady DC value, and the average is roughly 12 volts, as we expect. Now the switch node voltage down here, we can see that it's switching at a much higher frequency than the grid, and that's so you can reduce the size of the transformer. So if we zoom in, it's roughly switching at 40 kilohertz, and the value is what we'd expect for a flyback converter. So when the switch is on, the switch node is at 0 volts. When the switch is off, it's at twice the input voltage. And this is what you get for a flyback when the duty cycle is 50%. All right, now we can zoom back out and try to understand what's going on with this yellow output voltage. Now I said that this inverter is meant to emulate the grid, so we'd expect 120 volt RMS sine wave output. But in fact, this is a very cheap inverter, and so instead of including the necessary filtering components to provide that sine wave output, they omit those. So they just take the output of the enfolder and leave that as a 3-level square wave. And what they do is they adjust the width of the peaks such that the RMS of this waveform matches that of the grid. So you can see if we compute the RMS on the right here, it's roughly 120 volts. And this means that when you plug your devices into it, you'll have the same exact power provided as you would as if you plugged into the grid, although this one will have much worse power factor. And that's sort of the cost of using these cheap inverters. And it's actually fairly non-trivial to provide an output with a pure sine wave. And this is some of the research that the Robert Blawa group works on, designing high-performance converters with low distortion outputs. That's all for today's demo. Thank you for listening.